Welcome everyone. It is my honor to open this session on hybrid converter design, where I am going to kick us off by talking a little about some of the fundamental motivations behind hybrid power converter design, or more specifically, hybrid switched capacitor converters. To begin, here I am showing you a popular graphic that shows a survey of the relative energy densities expressed by both off-the-shelf inductors and multilayer ceramic chip capacitors. Here you can see that capacitors can often express energy densities up to 1,000 times that of their inductive counterparts, and as such, there is a strong incentive to use capacitors as our energy transfer elements. However, there is a catch, and that relates to hard charging losses. This problem ultimately cripples the ability of capacitor-based converters in fully utilizing their theoretically achievable energy densities. To illustrate how this hard charging loss works, consider what happens when you short a capacitor in parallel with a voltage source when the capacitor begins with a different voltage potential. Doing so causes an abrupt transient inrush of current as charge is rapidly redistributed. Now, please feel free to pause this video and work through these calculations if needed, but in summary, you can do some simple calculus and prove to yourself that any time you short two voltage holding elements together in this way, with different voltages stored on each, you end up burning a significant amount of energy in the switch's intrinsic resistance. Moreover, the larger the voltage difference, the worse your losses are relative to the amount of energy successfully transferred. Ultimately, when charging your capacitor from 0 volts, you see that equal amounts of energy are absorbed by both the switch and the capacitor. This is synonymous to a power converter with a dismal 50% efficiency. In order to retain reasonable efficiency, a purely capacitor-based converter must operate on the opposite extreme of this curve, where resistive losses are lower with respect to energy successfully transferred, but the energy transferred to the capacitor is itself also greatly diminished. As such, voltage ripple is kept very small, and this capacitor cannot come anywhere close to transporting the energy predicted by its theoretical limit. To shift our focus now to understanding how hybrid switched capacitor topologies are able to unleash a capacitor's true energy density, I find it helpful to consider the following problem. Here, just like before, if we close the switch, there will be a transient inrush of current and we will lose half of our system's energy. But now consider what happens if we add some small inductance into this loop. In this case, we have shifted to a second-order RLC circuit, and as our inductor increases in size, we begin to see oscillations in the settling response. If we increase our inductor further, the oscillations are more pronounced and sustained as we become truly underdamped with an increasing quality factor. Now, if time is allowed to go to infinity, our oscillations will dampen out and we will again lose half of our energy. But the premise behind a resonant hybrid switched capacitor converter is to terminate this progression prematurely. Instead, we reopen our switch at some critical point in time, and in this case you can see by simple symmetry that virtually all of the energy stored on C1 has been effectively transferred to C2, with very little energy loss, despite undergoing a very large voltage swing. The key takeaway here is that we can facilitate very effective energy transfer between capacitors if we introduce a very small assistive inductor which can change its voltage instantaneously to account for any voltage discontinuities, essentially choking out any lossy transient inrush currents. Do note that when this principle is used in actual hybrid switch cap design, these assistive inductors do not carry out the full voltage conversion and are simply there to help the capacitor that perform most of the work. Moving on, the converter I am going to show you is a specific hybridized variation on the commonly known Dickson topology. The Dickson topology was proposed in 1976 as a substitute to the commonly used Greinacher or Cockcroft-Walton topology, but within the context of a fully integrated circuit design. When building fly capacitors on chip, Dickson realized that the non-negligible substrate capacitance of a gate oxide capacitor was severely restricting the achievable conversion ratio in a Cockcroft-Walton topology, where distributed parasitics acted somewhat similar to bubbles distributed throughout a hydraulic system. Instead, Dickson's structure allowed all of these substrate capacitance to be collected together and driven with low impedance, ultimately allowing for much higher conversion ratios. However, in the discrete converter world, there is no substrate capacitance. So that begs the question as to why we should consider the Dickson topology over the tried and tested Cockcroft-Walton approach. Well, there is an answer to this, but first I think it's important for me to define what I consider to be a Dickson-type topology. Given their identical switch structures, note that the defining difference is in the capacitor networks. As such, I like to describe a Dickson-type network as one in which all fly capacitors contained within that network all share a common bottom plate. Conversely, in a Cockcroft-Walton network, fly capacitors are stacked on top of one another. Now, these two networks can be configured to give identical large signal voltage ripple responses as shown, but it turns out that the Dickson network can also be configured to express properties that the Cockcroft-Walton network simply cannot. For example, since each branch in the Cockcroft-Walton is stacked in series on top of the preceding arm, if we push charge into each branch, all branches must deviate by an amount greater than the branches below it, irrespective of capacitor sizing. This results in an unavoidable divergent ripple behavior as you travel up through the network, and this leads to problems when trying to smoothly dock these branches into other capacitor networks as part of a larger hybrid switch capacitor structure. Conversely, the Dickson can be made to mimic this same behavior, or if all capacitors are set equal, for example. In this case, we see that all branches increase by the exact same amount, and the relative voltages between each branch is maintained irrespective of the quantity of charge Q that is traversing through the network. In fact, the Dickson network can even be configured such that it exhibits a converging voltage deviation if desired. This versatility in shaping relative branch ripple relationships is a fundamental advantage that these Dickson-type networks can exploit. So with this advantage in mind, here is the proposed topology next to three similar topologies that can all benefit from the Dickson network's ability to shape favorable voltage relationships. You can see that the proposed solution has a switch structure that is identical to the more conventional hybrid Dickson shown in Figure A. However, similar to the dual inductor hybrid converter in Figure B, it now requires two inductors, although these are placed more similarly to the stacked ladder variant in Figure C. Each inductor is placed at the tail end of both capacitor networks, essentially forming an extended LC tank. Now, the LC tank property is important here. Topologies A and B do not have an isolated LC tank structure, and instead there are switching devices present on the nets that connect their inductors to their respective capacitor networks. Consequently, these switches experience the voltage ripple across the passives and must be rated to handle as much. This, however, is not the case for the proposed solution, where tank oscillations are hidden from neighboring switches and are bound only by the dielectric ratings of the passives themselves. As such, the highlighted nets can see a very large voltage ripple without increasing switch stress, and we are going to leverage this to elicit extremely high passive utilization. One additional advantage of this topology is that it can achieve two-phase operation with a 50% duty cycle while setting all fly capacitors equal, whereas topologies A and B require divergent capacitor sizings which degrade passive utilization at large conversion ratios. One last comment contrasting this topology with the stacked ladder is that the stacked ladder requires a bypass capacitor column with values theoretically infinite in size. However, in practice, much smaller values can be used when interleaving two such converters. But in doing so, you are almost doubling the number of required switches. As such, the proposed topology represents a greatly slimmed down version of the interleaved stacked ladder. Next, I will quickly run through the analysis of this topology. To begin, we can apply the well-established charge flow analysis technique and deduce that all fly capacitors conduct equal charge quantities in steady state. Since our capacitors are all equal in size, it follows that they all experience identical voltage ripple, as was the case in our earlier example. Next, we would like to assess our phase transitions and ensure that no voltage discontinuities exist that would lead to hard charging losses. To do this, we can draw out both phases, and here I have annotated the voltages stored on each capacitor, both at the start and end of both phases. For example, here you can see that in phase 2, capacitor C1 begins the phase with a positive delta ripple and concludes the phase with a negative delta swing, and all other fly capacitors behave likewise. Having set up the problem, we can now apply Kirchhoff's voltage law and obtain a set of equations that does yield a singular solution, verifying that no transient inrush currents will occur as we transition from one phase to the next, and that complete soft charging is achievable with two-phase operation. Do note that if this were constructed using Cockcroft-Walton type networks, no such solution would exist. Next, in order to deduce this converter's natural resonant frequency, it helps to simplify each phase into an equivalent AC model. Beginning with phase 2, we can short out DC sources and combine capacitors into one effective capacitance, as shown, and similarly for the inductor. Phase 1 is a little more challenging. In this case, once again, we remove DC offsets, and now, before we can simplify further, it helps for us to recognize a virtual ground, depicted here with a dashed gray line. This allows further simplification into two separate LC tanks, as shown. Now, having obtained these two equivalent AC models, we can recognize that if we set both inductors equal, in addition to all fly capacitors being equal, we see that all LC tanks exhibit identical natural resonant frequencies, irrespective of conversion ratio n, provided that n is in fact odd. Finally, since both phases resonate with the same time period, we are left with a resonant converter that desires a 50% duty cycle for precise zero current switching. A discrete 1 to 5 prototype was constructed that was designed for a maximum input voltage of 20 volts. A typical bootstrap circuit was used to provide power to the gate drivers of switches S2 and S4 as shown, and diodes were used for the remaining high-side switches. Diodes were used here for ease and simplicity in proving this topological concept, but also serve to illustrate their natural and unforced preference to adhere to a 50% duty cycle, as will be demonstrated in a moment. But first, this prototype achieves a peak efficiency of 94% and a maximum output power of 129 watts, largely limited by the diode's losses. But irrespective of this, this converter still achieved a very satisfactory power density, reaching over 5 kilowatts per cubic inch with a reasonable heat dissipation density of 64 kilowatts per liter when using forced air cooling. Next, we will show you a series of measured waveforms all taken while the converter was operating under heavy load conditions. Both switch nodes are complementary to each other, with switches 1 through 4 experiencing a voltage stress equal to the low side input voltage. Smooth sinusoidal inductor current waveforms demonstrate near zero current switching for reduced switching losses. Looking now at the internal tank node voltages, we see a 100-volt peak-to-peak voltage ripple, alluding to highly effective capacitor utilization. If we then plot the capacitor voltage waveforms, we see 80 volts ripple across each fly capacitor, verifying our expectation of excellent energy density utilization, with 2 of the fly capacitors even undergoing a periodic reverse bias as they are exercised over almost their entire dielectric range. Next, we plot the reverse voltage on each of the 5 diodes, depicting their reverse voltage stress over time. Despite very large tank ripple, the diode's blocking voltages are essentially flat and nearly identical to light load conditions. Moreover, we see that the conduction of each diode naturally and precisely aligns with its intended conduction period without being forced to do so by an external clock source. While fully synchronous switches could potentially mask any inconsistencies in soft charging capability by forcing a conduction period, here the diodes remove any doubt as to this topology's capability for complete soft charging with two equal phase durations, and indeed synchronous switches can easily be substituted in. To summarize, we believe this topology has significant potential with a long list of desirable attributes. Complete soft charging is achieved across all fly capacitors, with both fly capacitors and inductors all being equal in size, simplifying design effort and reducing cost. Current flow is evenly distributed throughout its components, further aiding in thermal design. Switch utilization is maximized due both to topology, load independence, and as a result of 50% duty cycle, which minimizes RMS currents. Additionally, the 50% duty cycle greatly simplifies control effort. Furthermore, passive utilization is also maximized with very high capacitor utilization achieved in practice. Last, while beyond the scope of this presentation, complete zero voltage switching in addition to some resilience to component mismatch is also achievable with a slight increase in switching frequency, as has been demonstrated in similar work. To conclude, we look forward to demonstrating a fully synchronous variant for step-down applications in the near future. And that's it. So thank you for your time, and please feel free to contribute any questions or comments that you might have. Cheers.